Welcome back to the lectures in chemistry on the atomic structure and chemical bonding. My name is Mangala Sundar and I am in the Department of Chemistry, Indian Institute of Technology, Madras, and my email coordinates are given here for you to communicate course related inquiries and things like that. Okay. Now, this is a continuation of the last lecture on the introduction to angular momentum. And in this lecture, let us look at the properties of the spin half system angular momentum. The electron spin is the most famous example. Proton spin, the nucleus proton, also has a spin angular momentum given by the angular momentum magnitude 1/2. So, this is the purely quantum mechanical spin property that we were studying. Now, in the last lecture, I think I left with the question on the commutation of the component commutation relations, basically relations of the components, relations between the components. I think we were looking at angular momenta with the following notation: S as the spin angular momentum, and in the coordinate representation given by three components Sx, Sy and Sz. The orbital angular momentum also given by the three coordinates with the corresponding symbols, and the total angular momentum, which is the sum of L plus S. L and S, the sum of L and S is Jx of x plus the corresponding components in the other directions. Okay. Now, the question that we want to address and also pursue further is the fact that the components Sx, Sy, the commutator between them is given by this relation IH bar Sz, and likewise the commutator of Sy and Sz is given by IH bar Sx, and Sx commutator is IH bar Sy. Okay. These are dimensioned angular momenta. The dimension is there in the H bar that you use. Therefore, for the logical development of some of the algebraic properties of them, let us define an angular momentum without the dimension, namely I as S by H bar, or L by H bar, or J by H bar, whichever that we want to deal with. Okay. We are going to deal with the spin angular momentum, and let us define I in such a way that if I is defined without the H bar, then it is immediate that the commutator Ix, Iy is I, Iz, Iy, Iz commutator is Ix, and Iz, Ix commutator is Iy. We shall use this as these as the starting point for all the algebraic properties that we study in this lecture. Okay. No H bar here. It is important to note that I square, which is given as the sum of the squares of the components Ix and Iy and Iz, I square commutes with all the three components. I square comma Ix commutator is 0, I square comma Iy commutator is 0, and I square Iz commutator is also 0. Okay. Therefore, because these are operators, angular momentum operators, and because they commute, it is possible to have simultaneous eigenfunction for the pairs but only one of the pairs, I square Ix or I square Iy or I square Iz. By convention, we normally choose the pair of operators for which the eigenfunctions are defined simultaneously as I square and Iz. The spin a half angular momentum corresponds to the following property. I square acting on this function, spin a half angular momentum, corresponds to two possible eigenvalues for the Iz operator. Okay. Iz acting on psi 1 gives you half psi 1, and Iz acting on the other eigenfunction psi 2 gives you minus a half psi 2. So, these are the two discrete values for the z component of the spin a half angular momentum, and I think we discussed this in the Stern-Gerlach experiment that was done in the last lecture. What about I square? I square on psi 1 and 2, whichever it is, okay, gives you the same result, namely I into I plus 1, and I in this case is 1/2, therefore, it gives you 3/4 on psi 1 or 2. It is the same value. Okay. So, we have a wave function psi 1 2 psi, which is defined by the same eigenvalue of I into I plus 1 for the operator I square, but with different eigenvalues half and minus a half for the Iz operator. The usual convention is to write psi 1 with these eigenvalues as the descriptors, namely the half for the Iz square, sorry I square, the half for the operator I square, where I into I plus 1, this one. So, this is half, and then the other half is the eigenvalue of the Iz operator. So, psi 2 will be 1/2 and minus 1/2, and the convention in textbooks and in the literature, physics literature, and also in the chemistry in the NMR and all these subjects, the convention is to write this as alpha and beta states, spin a half states. These are spin a half eigenfunctions with the specific properties as I have given here. I square on alpha or I square on beta gives you 3/4 alpha or beta. Iz on alpha gives you half alpha, and Iz on beta gives you minus a half beta. Okay. Now, while this is clear, what about the action of Ix on alpha, Ix on beta, Iy on alpha, Iy on beta? Because these are the other two spin angular momentum components, and even though they are not simultaneously alpha and beta are not simultaneously eigenfunctions of Ix and Iy, we must know what happens when Ix operates on alpha or Ix operates on beta, and likewise Iy on alpha or beta. To calculate this, there is a very standard method, namely to first look at the commutator, first define a pair of operators called I plus spin angular momentum raising operators. We will see why it is angular momentum raising operator, and the other one I minus as Ix minus Iy as the lowering operator. We'll see in a few minutes why these names raising and lowering come in. To calculate the effect of Ix on alpha, let us start with the commutator Iz comma I plus, and then act on the state alpha. But first let us look at the commutator. And that's easy to write down because it is Iz comma Ix plus Iy. And the commutator of z with x gives you Iy, it gives you Iy, and the commutator of z with Iy gives you, with y gives you minus Ix, and therefore with plus I into minus Ix, the answer is Ix plus Iy is equal to I plus. Okay. Therefore, the action of Iz I plus minus I plus Iz on the state alpha is the same as the action of I plus on alpha, and you can write this down immediately as Iz acting on the state obtained by the action of I plus on alpha minus I plus on the state obtained by Iz on acting on alpha, and that is of course 1 by 2 alpha. So, this 1 by 2, and that is equal to I plus on alpha. Okay. Therefore, Iz acting on this state is equal to 3 by 2 acting on the same state. What is the state? The state is the state obtained by the action of I plus on alpha. Therefore, Iz has an eigenfunction psi, which is this, which has an eigenvalue 3 by 2 on psi. That is not possible because we have started with the requirement with the properties that I plus Iz has only 2 eigenvalues plus and minus half, plus a half and minus a half. Therefore, the state Iz acting on that state giving you 3 by 2 the state is not a possible state for the operator Iz, which means I plus on alpha has to be 0. It does not exist. Okay. So, this is property 1. What about the same thing I plus on beta? You can do the same commutator, namely Iz I plus acting on beta minus I plus Iz acting on beta is the same as the I plus on beta, and you can see immediately that this gives you a minus a half, and therefore, you will get Iz on this state I plus on beta plus 1 by 2 I plus on beta, because this Iz on beta has already given you 1 by 2 times beta. Therefore, what is left over is this, and I plus on beta on the right hand side, which tells you that the two together gives you Iz acting on a state gives the result of 1/2 on that state. What is the state? The state is I plus operator acting on beta. Now, remember the eigenfunction of Iz with the eigenvalue half is alpha. Therefore, I plus on beta is equal to this, or it is proportional to this. Linear algebraic calculation tell us that the action of I plus on beta is alpha. Okay. The action of I plus on alpha is 0. So, if you think of alpha and beta are two states, you call this as alpha and you call this as beta, then you see I plus acting on the state takes it up, and I plus acting on the state takes it to 0, no further states. Okay. This is the action of the raising and raising operator on the alpha and beta. The action of the lowering operator by exactly the same argument is obtained by calculating the commutator I minus on Iz, and I will leave it to you to verify that this is the same as I minus, and therefore, you will get the relations I minus on beta is 0, I minus on alpha is equal to beta. Okay. So, you have that. Now, also remember that alpha and beta are two eigenstates of the Iz operator with different eigenvalues. Therefore, the states are orthogonal to each other. Alpha on beta is equal to 0. The states are normalizable, and therefore, we will use only those normalized states, namely alpha, alpha is 1, and that is equal to beta, beta. Okay. So, this is the orthogonality property of the eigenfunctions of the IZ operator, and the states are such that the action of I plus and minus operators on alpha or beta or what you have already seen. Now, therefore, what is Ix on alpha? Ix on alpha is I plus plus I minus by 2. Remember, Ix plus or minus Iy is I plus or minus. Therefore, if you add these two, you get this I plus plus I minus is equal to 1 by 2, and therefore, the action of the state on the state alpha by Ix is the same as that. And you know I plus on alpha is 0 and I minus on alpha gives you beta. Therefore, the answer is 1 by 2 beta. Okay. And Ix in a similar way acting on beta gives you 1 by 2 I plus plus I minus on beta, and I minus on beta is 0, I plus on beta gives you alpha, therefore, it gives you 1 by 2 alpha. Okay. So, the action of Ix on both the states are known, therefore, the algebraic details are becoming more and more complete. The only other thing that we need to know is the action of Iy on alpha and beta. Okay. Iy on alpha and beta can also be obtained in a similar way, because you already know the action of plus and minus on alpha. Remember, this gives you that Iy is minus I by 2 I plus minus I minus. If you subtract the one equation from the other, this is what you will get. Therefore, Iy acting on alpha is equal to minus I by 2 I plus minus I minus acting on alpha. I plus on alpha is 0, I minus on alpha gives you beta, and there is a minus and minus, therefore, it is a plus I by 2 beta. And Iy on beta is again minus I by 2 I plus minus I minus on beta, and I plus on beta gives you alpha, and it gives you minus I by 2 alpha. Okay. Therefore, summarize these, and immediately we can write to the matrices for these operators in no time here. Okay. Ix on alpha is half beta, Ix on beta is half alpha, Iy on alpha is I by 2 beta, and Iy on beta is minus I by 2 alpha. Therefore, in this representation of alpha and beta, what is the matrix representation for the operators Ix, Iy? If you recall the vector algebra and the linear operator space that we did earlier, it is alpha Ix alpha, this is for the Ix operator, and then it is alpha Ix beta, and this is beta Ix alpha, and this one is beta Ix beta. And you can see right away that alpha Ix on beta is given by this, okay, because this will give you, sorry, this is for Iy, and we have to look at this alpha Ix beta is this one. So, if you write alpha Ix on beta for this, then you do the same thing here, 1 by 2 alpha on alpha, and this is 1. So, the answer is 1 by 2. Okay. This is 0. Ix on alpha gives you beta, therefore, alpha beta is orthogonal. So, you have 0, keeping 1 by 2 outside, you have 1, 1, 0. Okay. This matrix sigma x, as it is denoted 0, 1, 1, 0, is the famous Pauli spin matrix, spin 1/2 matrix, x component. Okay. Likewise, for Iy, all I need to do is to replace the operator Ix with Iy in all 4 places, and Iy on alpha gives you here, you have seen that, gives you beta, therefore this is 0. Iy on beta gives you alpha, and therefore that is, you can see that Iy on beta gives you minus I by 2 times alpha, therefore this matrix Iy turns out to be 1 by 2 0 minus I 0, okay. And this is again famous Pauli spin matrix, half matrix Y component. Okay. What is the Z component? That is easy, because Iz on alpha gives you half alpha, therefore this element is 1 by 2 alpha alpha, and it is 1 by 2, and again alpha on Iz on beta is therefore 0, because this gives you beta back, and orthogonality makes this result go to 0, and beta Iz on alpha is also 0, beta Iz on beta is minus 1 half. So the matrix representation for Iz is 1 by 2 0, sorry, 1 by 2 1 1 0 0 minus 1. This is the sigma Z, 1 0 0 minus 1 is equal to sigma Z, the Z component of the Pauli spin matrix. One half matrix. Okay. So these are the properties of the angular momentum operators for a spin a half system. Since we know all the spatial components Ix, Iy, Iz acting on alpha or beta, the 2 eigenstates for the problem, what they give, we have complete knowledge of spin a half system with respect to the algebraic details. Okay. Now to close this lecture, you recall in one of the earlier problems we were looking at sigma x sigma y plus sigma y sigma x, and you can see right away that sigma x sigma y gives you 1 by 4, sorry, there is no 1 by 4, this sigma x is just a matrix. Okay. It gives you 0 1 1 0, and it gives you 0 minus I 0, the product of which is I 0 0 and minus I, and the product sigma y sigma x is 0 minus I 0 times 0 1 1 0, and that is equal to minus I 0 0 plus I. Therefore, this is equal to minus sigma x sigma y, therefore this sum is equal to 0, and it is also easy to see therefore that sigma x sigma y minus sigma y sigma x is going to take the difference between these two operators, namely I 0 0 minus I minus I 0 0 I. So it gives you 2 I times 1 0 0 minus 1, so it gives you 2 I sigma Z. Okay. So the Pauli spin matrices have a numerical coefficient of 2 in front of an otherwise a spin angular momentum x or y or z component. So this is a very famous relation called the Pauli, this famous statement that we have, that the Pauli spin operators anti-commute, meaning that if you take the plus combination they go to 0. That is the negative of the commutator, therefore it is called anti-commutation. And it is not just x and y or z, it is cyclical, therefore the similar relations that you can verify are sigma y sigma z plus sigma z sigma y, that is 0, sigma z sigma x plus sigma x sigma z is 0, and sigma y sigma z minus sigma z sigma y is 2 I sigma x, and likewise sigma z, sigma x minus sigma x, sigma z is 2I sigma y. Okay. One last thing, namely sigma square is sigma x squared plus sigma y squared plus sigma z squared, and this you know is 0 1 1 0 squared plus 0 minus I 0 squared plus 1 0 0 minus 1 squared. The answer is 2 times here. This will give you 1, this will give you 1. The answer is 3 times the identity matrix 2 by 2, because this will give you 1 0 0 1, this will give you 1 0 0 1, this would also give you 1 0 0 1. So, it is 3 times the identity matrix. Therefore, sigma squared is equal to the operator 3 with the identity. Okay. So, these are angular momentum properties that we need to know for a spin a half system, and in the next lecture we will see the angular momentum for two such electrons or two such spin a half systems. How do we define them when the two spins interact with each other strongly, or when the two spin systems interact with each other weakly, and this is extremely important in establishing what is known as the antisymmetric state for two identical the spin systems of spin a half, namely the electrons as an example are two protons, and this will also just give you some insights into the famous principle that Pauli came up with, namely the principle for the antisymmetry and the principle of what is called exclusion, mutual exclusion, which is important in the study of atomic structure. Okay. We will do more of this with the two spins in the next lecture. Until then, thank you very much.